Alright, so in the last video we talked about our first and second periodic trends, which was our atomic radius or size of the atom and the ionic radius or size of the ion. In this lesson we're going to start by talking about ionization energy or the ionization potential. And that's going to be the amount of energy that is needed to remove an electron in what is called its ground state. So if we looked at the electrons where they're normally located, that is known as the ground state. If we put in energy and cause those electrons to move up or down, that would be called an excited state when they move up. But here we're just talking about its normal ground state. No matter the atom, even if we say, ooh, this atom wants to lose an electron, we use that language sometimes, every atom requires energy to remove an electron from it. Even if it is more favorable to lose an electron, it still takes some amount of energy to remove that electron. So let's look at how much energy it takes and how that changes. As we go up the periodic table, the energy that's required to remove an electron increases. And the reasoning is shown over here on your left. So as we go up the periodic table, it takes more and more and more and more energy to remove that electron. Of course, the reverse is true. As we go down the periodic table, the amount of energy required is going to decrease. And both of those things have to do with the energy level of the valence electrons. So remember, we have the nucleus in the center, and then we have these electron orbitals that get bigger and bigger as we go down the periodic table. So as we go down the periodic table, these electrons are further and further from, I like to call this mama nucleus. So mama nucleus is positive, and she's pulling in her negative electron babies closer, right? But if they're further away, she has less pull. So they are easier to remove. So it's going to take less energy. But if an electron is in here, close to the nucleus, then it's going to take more energy to remove it. So as we go up the periodic table and the atoms get smaller, it's going to take more energy. Down the periodic table, as they get larger, it's going to take less energy to remove those electrons. A similar argument can be made as we move from left to right. As we move from left to right, the ionization energy, or the energy required to remove an electron, increases. And this is because we're adding more protons. So that nucleus, that mama nucleus in the center, is getting more and more and more positive. So that's a stronger pull on those outside electrons. So you can think about if your mom is like a bodybuilder, it's going to be hard to kidnap you from her because she is going to tackle, right? Whoever tries to. But if your mom is like a wimpy, I don't know what a wimpy example would be, but not very strong, then it's easier to remove the electron or kidnap the child, so to speak. So as we move across, the ionization gets bigger because we're adding more protons. All right, you can see that graphed here. They love this graph on different tests and AP exam and stuff. So you can see as you go from hydrogen to helium, that's moving across the periodic table. So your ionization energy goes up. And then when you go down to a new row, lithium is on a second row. So we drop way down. And then we go up as we move toward neon because we're moving across. And then we go down when we go to the next row. And then up as we move across that row. Then down to the next row. And up as we move across that row. Down to rubidium, row 5, and up as we move across to xenon. Now see that there are some exceptions, and they're highlighted in green. And these exceptions show us areas where we think it should be increasing, but it actually drops. So you can see there. As we move from beryllium to boron, we see a drop. As we move to aluminum, from magnesium, we see a drop. Zinc to gallium, we see a drop, and cadmium to indium, we see a drop. We should notice something there, though. Each of those drops occurs as we move to group 13. All right, there's something going on at group 13 that's an exception. All right, so here is some further explanation of this. Generally, we increase as the radius decreases. So remember, we talked about how the radius gets bigger as you go down, but the ionization energy gets bigger as you go up. And the radius gets smaller as you go across, but the ionization energy gets larger as you go across. So in general, ionization energy and radius are going to be inverse. As the radius gets smaller, your ionization energy is going to get larger, because as the atom gets smaller, you've got a stronger force of attraction between that nucleus and those valence electrons. However, there are a few exceptions, and one is at group 13. And in group 13 is when we go into the p, right? So that's why there is an exception there, because it's taking more energy to pull the electron from the full d than just that one in the p, or from the full s than that one in the p. So really it's because we're moving into this new sub-level, okay? And as we move into that new sub-level, we have boron, aluminum, gallium, indium, thallium. In that new sub-level, that single electron that we're trying to remove in that p sub-level is easier to remove because it's the only electron there. It has more energy than the electrons in the full sub-level. And by energy, we're talking about these energy levels away from the nucleus, right? So that p sublevel is a little bit further from the nucleus with its one lone electron, so it's a little bit easier to remove. So even though we think it should be increasing as we move across the periodic table, when we move into that p sublevel, we see an exception to the rule. All right, now this is discussing what if we want to remove 2 electrons. That second electron that you would want to remove is called the second ionization energy. And the second ionization energy or ionization potential is always greater than the first. So you remove one electron and then you want to remove another. That second removal is always more difficult than the first, because when you remove one electron, the atom gets smaller. So now you're trying to remove an electron from an even smaller atom, and so it's more difficult. And the explanation is in blue here. Your radius is reduced once your first one is removed, and now you have more protons than you have electrons. So the pull from the nucleus is even greater than it was before. Every single element, though, has this one electron that shows an extremely large increase in ionization energy. And that is the electron that comes from the previous energy level, okay? From the previous energy level. So when it says principal quantum number, that's just talking about energy level, all right? And we'll look at an example of that. Alright, I want you to look with me at some different elements and their different ionization energies. So you see up here the first ionization energy for lithium, beryllium, boron, and carbon. And these are on the second row and we're moving across. So as we move across, the ionization energy, we expect it to increase. Except when we move into that p sublevel, we see that small decrease, that exception. But in general, we're increasing as we move across. Now let's look at the second ionization energy. So that would be to remove the second electron. Look how much bigger lithium's is than any of these others. Because lithium only has one valence electron, or one electron on the second level. So if you want to remove another electron from lithium, you've got to go to an inside sublevel. Remember, we're talking about the atom, and they're all on the second row. So they all have these 2 levels, but lithium only has one electron out here on the second level. So to get a second electron from lithium, you've got to go inside, and that takes a lot more energy. All right, let's look at beryllium. It has 2 outer electrons. So we remove the first, and then it is more difficult to remove the second, but then look at this huge jump that takes place when we try to remove the third. So we can tell that beryllium's third electron must be on the inside, and these two are on the outside. For boron, we go 800, then it gets more difficult with the second, more difficult with the third, but look at this huge jump that takes place when we try to remove the fourth, because boron's fourth electron is in an inner shell. You can kind of follow the trend. Carbon, we got 1, 2, 3, 4. Notice it does get more difficult, but we're still staying within sort of the same range of numbers, and then boom, jump way up to 37,000 if you want to remove carbon's fifth electron, because carbon has 4 on its valence shell. So that's what we mean by removing subsequent electrons. The first is going to be the easiest for every single atom, and then they're going to get more difficult, but we're going to see a huge jump if we try to take away an inside electron. For these last two, you need to be aware of their definition and their trend, but we won't go as in depth as we have into radius and ionization energy. So make sure you are extremely familiar with the first two. You know them backwards and forward. You know why they occur. And for these last two, make sure you know the definition and the trend. The first of these last two is electron affinity. Electron affinity is the energy change that occurs when an electron is added. So for ionization energy, we're taking away electrons. But here we are adding electrons to form a negative ion. This is a measure of how much an element wants to accept an electron. So on ionization energy, we're trying to remove an electron. That always takes energy. But here we're going to try to give the element another electron. And this is going to be a measure of how much they want to accept it. Electron affinity can be negative or positive. Remember, ionization energy is always positive. It always takes energy to get that electron off. But adding an electron can be negative if it releases energy. If the electron affinity is negative, that means that the atom wants to accept an electron, and when it does, it's going to give you energy back. Okay, because it's favorable for that to happen. So the atom's going to take the electron, and as a thank you, it's going to give off energy. The more energy it gives off, the more negative, that's all that negative means, is that it's giving off. The more negative, the more it wants that electron. However, if the value for electron affinity is positive, the atom does not want to accept that electron. Okay, so here's what that looks like. It's the same trend as ionization energy. As you move across, it becomes more negative or increases. And as you move up, it becomes more negative or increases. However, two exceptions. This group right here does not want to gain another electron. So they have positive electron affinity values. And group 18 does not want to gain an electron. So they have positive electron affinity values. All these other values are negative, and they get more negative as you go across and more negative as you go up. Okay, last term is electronegativity, which is very similar. This is the ability of the atom to attract the electrons. So we're not giving it the electron, we're seeing how able or how strongly can it attract the electron to itself. So we're just putting electrons around it and seeing how strongly they pull the electron in. This happens inside a chemical bond. So we'll bond two atoms together and see where the electrons spend more time. The electrons will spend more time around the more electronegative element. So we know that element is attracting the electrons to itself more so than the other element. All right, and here's the trend. The electronegativity increases as we move across. These smaller atoms, remember you get smaller as you move across, smaller atoms can attract electrons to themselves better because the nucleus is closer. It also increases as you go up for the same reason. Smaller atoms can attract the electrons to themselves more easily than large atoms. However, group 18 has no electronegativity values. Okay, they just don't exist because this group does not form a bond. And electronegativity occurs within a bond as the atom attracts the electrons to itself. Alright, so we have 4 trends, 5 if you include ionic radius. Be aware of what they are, the definitions for the terms, what the trends are, do they increase or decrease across, and then why.